Let's see, where did we leave off? Maybe we start, oh, Harry just answered. Why don't, Precious, I have a question for you, Precious. Are you ready to listen to my question?
Yeah.
All right. So this is the question. I can't remember the question. I'm thinking about it. The question is this. This is what the question is. And we've asked this question before. But what is temperature? When we express information about temperature, what are we really talking about?
How fast the molecules are moving?
That's right. The movement of the molecules. Or another way of saying it is the kinetic energy of the molecules. The kinetic energy of the molecules. Okay? Precious, do you remember any equations for kinetic energy, maybe from an old physics class? I think we talked about it maybe once in 105, and it wouldn't be a problem if you don't remember. Do you remember any equations for kinetic energy? Kinetic energy.
I don't think I remember.
Okay. 1/2 mv squared. Does that look familiar at all? Sarah, does that look familiar? Have you heard of that before?
Doesn't look super familiar, no.
Okay. So this is a traditional statement of the kinetic energy of a system, where m is the mass of whatever thing you're looking at, and v is the velocity of that mass. So the kinetic energy, or the energy of motion of the material, is identified as 1/2 the mass times the velocity squared. All right? So we can also use this to talk about the kinetic energy, or the how fast the molecules are moving, the gaseous molecules are moving. All right? So if I have two gases, all right, let's say I have nitrogen gas and argon gas. Whoops, start over. Nitrogen gas and argon gas. Okay. Which one of these gases is heavier? Brielle, which one of these gases is heavier? Let's bring up our periodic table here.
I'm not really sure.
Well, the molar mass of N2, do you know what that is?
It's 28.
Yeah, 28. 2 nitrogens, 2 14s. Very good. What about the molar mass of argon?
It's 40.
40. Okay. So the molar mass of N2 is 28. The molar mass of argon is 40. That's how many grams there are per mole of that material. All right. So if I have a system, there it is, a balloon, and if I have in this balloon nitrogen gas and argon gas, and they're at the same temperature, right? At the same temperature, that means they have the same kinetic energy. So the kinetic energy of the nitrogen gas is equal to the kinetic energy of the argon. Because they're at the same what, Jace? Why are their kinetic energies equal, Jace? What did I say?
Was it because they're in the same confined area?
Well, it's because they have the same temperature.
The same temperature?
Because temperature defines a gas's kinetic energy. It's a definition of the motion of whatever the system is, and for a gas, it's telling us how much energy of motion those gases have. Okay. So the kinetic energy. Go ahead.
Oh, so does that mean the nitrogen is going to have a faster velocity if they're equal to one another?
It will, because if I look at 1/2 mv squared for, let's say this is the nitrogen, that's equal to the 1/2 mv squared for the argon, right? And because the mass here is 28, the 1/2s cancel out, so I don't have to worry about them. But the mass here is 28. The mass here is 40. This is the mass of, sorry, this is the velocity of the nitrogen. Oops, zoom in here a little bit. Ugh. Gotta buy a different camera. The mass of the nitrogen is 28 grams per mole. The velocity I can describe as V of the nitrogen gas here, right? The mass of the argon, 40, and I can describe the velocity here as the velocity of the argon squared, all right? So then if I wanted to compare the velocities of these two species, the velocity of the neon gas, sorry, not the neon gas, but the nitrogen gas squared over the velocity of the argon gas squared, I could set that equal to, I have the 40, which is the mass of the argon, over the 28, which is the mass of the neon. And I have an equation here that allows me to relate the mass of the material of the different gases in that confined location at the same temperature. Their masses, I can relate those to the velocities of those different gases. If I can rewrite it also where I take V of the nitrogen gas over the velocity of the argon, and that is one whole quantity squared, equal to 40 over 28. And then I can go one more step and take the square root of both sides so that I have the velocity of the nitrogen gas over the velocity of the argon being equal to, this here is the, what's the 40 here, Landon? What's that 40 again?
Argon.
Yeah, the mass of the argon, right?
Yeah.
Over, what's the 28, Landon?
The mass of the nitrogen.
Mass of the nitrogen, square root. So I have the ratio of the velocities is equal to the square root of the ratio of their masses. Now here the argon's on the bottom and here the argon's on top. But what I'm learning here is how fast, and the relative relationship of how fast molecules can move is related to this relationship, is defined, is identified by this relationship. Okay? So let's bring up our slide again. If I have a bottle of perfume, right? Here's my bottle of homemade perfume that I make, right? I set it on the table and I open it up. I open it up. If I just leave it there all day long, eventually it's going to, here first, start smelling good, and then it's going to spread all the way to every corner of the room until somebody walks in and says, "Woo, Brother Scott smells good," right? They're going to be able to smell this perfume because it slowly, what we call, diffuses into the room. And how fast it diffuses will be related to how fast it can move, and its motion will be related to the mass of the molecule of that gas. Okay? So here's a question for you then. Who do we got? Landon, Robert's turn. Robert, if I had some nitrogen and argon gas in this bottle, and I opened it up and I said, go. And the nitrogen and argon are going to race to the other side of the room. Who would win, the nitrogen or the argon?
Definitely the nitrogen.
The nitrogen, right? The nitrogen has a smaller mass. Therefore,
Correct.
the fact that they have the same kinetic energy would cause the smaller one to be moving faster. So when we talk
Right.
about relative rate of material, they have the same kinetic energy, but because the masses of some gases might be larger, that larger mass will slow down the actual velocity of the chemical. Diffusion is what we call it when one gas is leaving a vessel and moving across in a container through another gas. And that's what's happening when I open a bottle of perfume. It has to move through all this atmosphere of nitrogen and oxygen in my room. Diffuse is when I open up a container into a vacuum. In both cases, the smaller gas, smaller mass of the gas with the smaller molar mass will move faster. And here is this relationship. The effusion rate of gas B over the effusion rate of gas A will be equal to the square root of the ratio of molar mass A over B. And you saw how we derived that, right? That comes from the kinetic energy of those materials. And then we have a few problems which we'll finish up talking about in class on, we'll probably just answer maybe one or two of these. But that essentially ends our chapter 11. So the next class, we're going to be starting chapter 12. All right, hope you guys learned something. If you